Oh, hello there. I'm Bulchen, a cute bear.
Hey there. I'm Nimikung, a cute bear. And this yellow one here is Jujmu Goku no Sir Ka Keijara Suichaya no Suijimitsu.
It's Genevieve Evangeline. My name is already long enough, so don't make it any longer.
Oh, sorry.
This time we'll delve into the most fundamental concept in mathematics. The approach called Axiomatism.
Yes.
Yeah.
So Venchan out of the blue, but if asked what's mathematics, so can you explain?
It's the study of numbers.
It tends to be misunderstood. But mathematics isn't the study of numbers. It's the study of logic.
What do you mean?
To put it simply, for example, in middle school, you do geometric proofs like this, right?
When you put it that way, geometry isn't necessarily about numbers, but we do it in math.
Oh, that's right. What these proofs are doing is starting from assumptions, following a strict logical development to derive a conclusion.
So doing logical development is what you call mathematics?
Simply put, yes. If you're logically developing something, regardless of the topic, that's mathematics.
By that logic, can anything be considered math?
Good point, Vincent.
He.
Oh. Yes, but there's one big condition. The subjects or claims we are logically developing must be perfectly formulated to a level where there is absolutely no ambiguity.
What do you mean by formulated?
That is, whatever is the subject, what operations can be performed on it, and what results when you do so. Rules are set, kind of like simple operation puzzle, and they are strictly or objectively defined.
So there's no ambiguity at all?
Exactly. That's right.
But in math, isn't it not just about proving with logical development? Don't we also do simple calculations like 5 plus 3 equals 8?
Good question, Nimikon.
He.
Oh. Things like 5 plus 3 equals 8 are mathematical statements that say 5 plus 3 and 8 are equal. And like this, they can be properly proven.
Well, even something like that has a proof.
Well,
No need to mimic me.
just now, I was genuinely impressed.
Are you sure you weren't copying me? My bad, genuinely.
Oh.
What does this proof do?
To understand that first, you need to understand how natural numbers and addition of natural numbers are rigorously formulated. Like this.
Oh, that's impressive.
Oh. I'll explain it step by step.
This is exciting.
Oh. First off, undefined terms are like words used to represent things or statements in a strictly formulated manner.
How are they different from ordinary words?
Ordinary words have inherent meanings, but that can lead to ambiguity. So undefined terms don't have any inherent meaning. Instead, through axioms, you precisely determine how you can use those words, and consequently their meaning is established.
What do you mean?
For example, when describing Venchan, even if you don't explain the meaning of Venchan, and say Venchan is a cute bear, or Venchan is yellow, or when Chen is small. You'd get an idea of what when Chen is like.
I see.
Well, I'm only a little small.
Oh, I'm sorry. But I think it's cute.
She's blushing.
You didn't have to say that.
Oh. So, as words that in themselves don't have any meaning, we'll be using the phrase such and such as a natural number, the word one, and the phrase the next of such and such. Here.
For example, does this word one have a different meaning from the one we usually use?
Well, in the end, the meaning is the same, but in order to define its meaning perfectly and rigorously, we don't think of the word one as having its own meaning, but instead define its meaning indirectly by rigorously determining how we use it. That's the idea.
I see.
So these axioms essentially determine the meanings of words, right?
Exactly. That's right. Axioms are claims that determine the substantive meaning of words. That's one way to explain it. Or to put it more simply, they serve as the starting point for logical development. The initial claims we acknowledge as true.
In math, can we just assume something is true without proving it?
Great question. We can't prove anything without some assumptions, can we?
Well,
let's say you need an assumption for that proof. If you need to prove that assumption is true, then you would need another assumption for that proof, right?
I understand.
And if that proof requires an assumption B, like that, you end up never being able to prove anything, right?
Why?
So, what do we do?
That's why we decide on some claims to accept as true without proof. Those are axioms.
So, and then, what is mathematics?
Starting from the claims we deem to be true, or axioms, mathematics derives various other claims through logical development. That's why it's a study of logic.
By saying deemed to be true, does it mean that axioms are essentially like assumptions?
Yes, exactly. Axioms, in other words, aren't like the temporary assumptions we mentioned in the geometric proof discussion, which are specific to a particular shape and are used only temporarily. It's an assumption used in a broader context. I can explain it that way too. This assumption, as opposed to the one that defines what kind of shape this is. The so-called axiom we're thinking about right now is an assumption that defines what natural numbers are. So, simply put, it's an assumption we always use when dealing with natural numbers.
I totally get it now.
I see.
So specifically here, the claim that one is a natural number, and if something is a natural number, then its next is also a natural number, are considered as axioms related to natural numbers. The first one is straightforward, so it's easy to understand, but do you understand what the second one is saying?
I think I do. Maybe.
So you don't get it, pal.
Do you get that, Ben-chan?
I think I do, maybe. Don't mess with me.
Or from the first axiom, we can say that one is a natural number, and from the second axiom, if something is a natural number, its next is also a natural number. So we can say the next of one is also a natural number.
By any chance, by next of 1, do you mean 2?
Yes, exactly. The term 2 will come up later, and next of 1 is a precise formulation of the common concept of 2.
Oh, I see. Since the next of 1 is a natural number. And if something is a natural number, its next is also a natural number. By using that rule again, we can also say that the next of 1 is a natural number.
I see, so that would be 3, right?
Both of you, well done.
He.
He.
Or in the same way, since the next of 1 is known to be a natural number, using the second axiom again, we can deduce that the next of 1 is also a natural number, which essentially means 4. And now that we know that the next of 1 is a natural number, in this manner, 1 the next of 1, next of 1, next of 1, and so on for every such item, we can derive that it's a natural number.
So these 2 axioms indirectly define the meaning of the word natural number, right?
Exactly, that's right. And they also indirectly define the meanings of 1 and the next of circle. The first axiom determines that 1 is the starting point of what's called natural numbers. And the second axiom creates the next point in a chain from that starting point. That's the idea.
Oh, I see.
I totally get it.
But practically speaking, it'd be a hassle to keep calling the number representing 4 as the next of 1. So next of 1 is called 2. The next of 1 is called 3. The next of 1 is called 4. And so on. It's easier to give them different names to call them.
It's clear now.
Just so you know, what we did now is just giving easy to understand names, and it has no particular mathematical significance.
So it's really just about making it more understandable.
Exactly. For now, we've finished formalizing the very concept of natural numbers.
Well,
So even simple numbers like 1, 2, 3, 4 can be explained this rigorously. That's what you're saying.
you didn't have to say that.
It's the other way around from usual. Now it's about defining addition between natural numbers.
This is a definition, not an axiom, right?
Yes. To sum up the conclusion, 5 plus 3 is essentially saying it's 8. So it's just defining what this and that plus this and that means. In that sense, it's like giving another name to numbers. Not adding any claim that's considered correct. It's just a definition in terms of wording.
But by the looks of it, it seems as complex as the axiom.
In fact, that's really the case. Even though it's the same definition. On one hand, it's really just giving another name, while on the other, it's creating a new concept called addition. This is just an image to be exact. Both are just definitions, in other words, giving another name to something.
What exactly is the definition?
First off, the ultimate goal of this definition is to rigorously define what natural number the from circle plus triangle represents, so that it yields the same result as the regular addition we use every day.
Of course, I understood that.
Now are you lying?
I just got in now.
So focusing on the triangle part of circle plus triangle, whether triangle is 1, or if triangle is something other than 1. We define it based on that.
I understand the first case where the triangle part is 1. But in the second case, it says after the plus is the next of circle. Does that mean it's something other than 1?
Good question. To give the conclusion first, the answer is yes. Fen-chan, when we think normally, what are the natural numbers other than 1?
If we think normally, are they 2, 3, 4?
Yes, that's right. So, those numbers like 2, 3, 4, in the formulation we're considering, how would they be represented without using abbreviations?
Well, 2 is the next of 1. 3 is the next of the next of 1. 4 is the next of the next of the next of 1. And so on. Well, right, every number other than 1 is the next of some number, so a natural number in the form of the next of square actually means any natural number other than 1.
Exactly, spot on. So firstly, if the triangle in Circle-Laplace triangle is 1, it ultimately means we are adding 1 to the natural number represented by circle. So the definition is simple. The meaning of Circle-Laplace triangle is the next of circle, right?
I see.
It feels like we're representing the concept of addition based on our prior understanding.
Yes, that's exactly it. Then next, we're looking at when triangle in Circle-Laplace triangle isn't 1. This one's a bit tricky, but as Fen-chan guessed earlier, anything other than 1 can always be expressed as next of. So the meaning of Circle-Laplace next of square is next of Circle-Laplace square. That's how we'll define it.
Oh. While defining the meaning of addition, there's addition in the definition itself, isn't there?
That's a great point.
Hee.
Or I think it'd be easier to understand with an example rather than explaining. So, as I was saying earlier, I'll think about proving 5 plus 3 equals 8.
What?
So we're coming back to this topic.
Oh, yes, we are. Firstly, the 3 in 5 plus 3 was a shorthand for next of 2. So first, you can transform the expression to 5 plus next of 2. Then, when you have 5 plus next of 2, based on the second definition of addition, you can transform it to next of 5 plus 2, right? Next of 5, if we use shorthand, is 6. So you can transform it to 6 plus 2. Looking back at this flow, and reconsidering the second rule of addition, in essence, the meaning of an addition like 5 plus 3 is similar to 6 plus 2, where you increase the number on the left by 1 and decrease the one on the right by 1. That's what it means. Look back at the original rule carefully.
Write the meaning of Circle-Laplace x of square is next of Circle-Laplace square. Given that rule, it indeed means increasing the left side by 1 and decreasing the right side by 1.
If we talk about it intuitively, even if you add 1 to the left and subtract 1 from the right, the sum doesn't change, so I understand that this kind of transformation is okay, but what's the point in doing that?
Good question. I think you'll understand if we continue with the proof. The flow of this part is exactly the same as before. 2 is shorthand for next of 1, so we can transform it into 6 plus next of 1, and using the second rule of addition definition again, it can be transformed into next of 6 plus 1, and next of 6 can be represented as 7 using shorthand. So it can be transformed into 7 plus 1, right?
I get it, but what's the ultimate point?
Just focus on this last transformation. Starting from 5 plus 3. Applying the rule of adding 1 to the left and subtracting 1 from the right. You sit here as well. And because of using it here, the number 3 on the right eventually becomes 1. And it's now the first rule of addition definition's turn.
Oh,
Really?
When we apply this rule, the next of 7 form, which doesn't involve any more addition. Then using shorthand, 7 plus 1 can be represented as 8 and the proof is done.
I see, so in the end, using the first rule of addition definition to derive a specific number not in the form of addition, use the second rule multiple times, like passing a button.
Exactly like that.
I see. The two rules cooperate to define what addition is, right?
Both of you understood it well. In this way, many people think of it as just calculation. But something like 5 plus 3 equals 8 is actually a mathematically provable claim.
I'm really convinced.
And then, when you ask what math is, it starts from axioms, the initial assumptions, then logically derives various claims. In other words, proving things. That's what it means.
Oh, I see.
This kind of. Let's only do things where we clearly define the axioms we use and from there logically derive something. This way of thinking is called axiomatism. Modern mathematics is research based on the principles of axiomatism. Mathematics is a discipline based on axiomatism. You could say.
I've come to understand the concept of mathematics well.
I'll review thoroughly with Jujmu Chen.
It's Fan Chan, isn't it?
Or